Welcome student to our online chemistry class. Our topic is halogen derivative. Now let us study the mechanism of Sn reaction. Now what is the meaning of Sn? We will start from that word. S for substitution, N for nucleophilic. So this meaning and the terms involved in that we already discussed. Now can you recall some concept? What is meant by order and molecularity of the reaction? So for that purpose, or to check the concept of this word from topic chemical kinetics. We'll go to chemical kinetics and let us see the order of the reaction. So let us consider the reaction A moles of A react with B moles of B, use C moles of C and D moles of D as a product. So if you apply the rate law for this equation, and from that the rate of the reaction can be written as rate is equal to K into concentration of A raised to X into concentration of B raised to Y. Then let us suppose that out of the A mole, X mole of A react, and out of the B mole, Y mole of B substance will react. Then the sum X plus Y gives the overall order. So order of the chemical reaction is given as the sum of the power of the concentration terms in the rate law expression. So one example is given: 2H2O gas gives 2H2O liquid and O2 gas. So experimentally determined rate law is equal to K into concentration of H2O2 raised to 1. So it is a first order reaction. If another equation is studied, H2 gas plus I2 gas gives 2HI gas. So rate of reaction is equal to K into concentration of H2 into concentration of I2. So here if we take 1 plus 1, then this reaction is, rate of the reaction is a first order with respect to H2 and I2. So overall order of this reaction is second. So I think all of you understood the order of the reaction. And what is molecularity of the reaction? So number of molecules involved in the equation is called as molecularity. So molecularity of the first reaction, A moles of A plus B moles of B gives C moles of C plus D moles of D is A plus B. That is molecularity, but X plus Y is the order of the reaction. For 2H2O2 gives 2H2O plus O2. The molecularity is 2, but order of the reaction is 1. So I think all of you understood this concept. Now we again go to next question. What is meant by mechanism of reaction? So stepwise description of a chemical reaction is nothing but mechanism. So in the previous table, (10.3), we studied the different reactions, and in all these reactions this X get replaced by the nucleophile and we get a product, and that X react with the positive part of your reagent and it gives the byproduct. So there are various reactions in which all the nucleophile substitute the X from your alkyl halide and they give the product. So these reactions are nucleophilic substitution. So halogen atom gets detached from the carbon and new bond is formed between that electrophilic carbon and nucleophile. So your covalently bonded halogen is converted into its halide as a leaving group and it reacts with positive part of your reagent and that gives a byproduct. So what is leaving group? Leaving group is a group which leaves the carbon by taking away the bond pair of electron. That's why that halogen carrying negative charge. It goes along with electron pair. And the reactant, alkyl halide, is called a substrate. The substrate undergoes two changes during this Sn reaction. The original CH bond undergo heterolysis, unsymmetrical breakage, and new bond is formed between the carbon and your nucleophile using the two electrons of your nucleophile. So nucleophile is negatively charged or it contains lone pair of electron. So these changes may occur in one or sometimes more than one step, and this description regarding the sequence and the way in which these two changes takes place in your nucleophilic substitution reaction, that is Sn reaction, is called as the mechanism of the reaction. So to study the or to write the mechanism, we must familiar with the kinetics of the Sn reaction. So let us study there are two types of Sn reaction, Sn1 nucleophilic substitution unimolecular and Sn2 nucleophilic substitution bimolecular. So let us see first Sn2 mechanism. So the reaction between methyl bromide and the hydroxide ion to give methyl alcohol and the bromide ion. This is a one nucleophilic substitution reaction. So let us see the rate of this reaction. So if we observe the kinetics of this reaction, rate of the reaction is depends on both this methyl bromide, that is substrate, and OH minus, that is nucleophile. So as a rate of the reaction is depends on both substrate as well as reagent or nucleophilic part. So that's why it is nucleophilic bimolecular substitution or Sn2 reaction. So rate of the reaction is equal to K into concentration of methyl bromide into concentration of OH minus. That's why it is Sn2 reaction. Now let us consider the detail about this reaction. Rate of this chemical reaction is influenced by the chemical species which are taking part in the slower step of this mechanism. So if you observe the above reaction, this reaction is carried out in single step, and that single step is also a slow step. So always we write the rate with respect to that slower step. So this indicates that there are two changes. One is bond breaking and another is bond forming. Breaking of bond between carbon and halogen and formation of bond between carbon and OH group, that is nucleophile. Both these takes place simultaneously, and it can be shown in your diagram. So there is a simultaneous attack of nucleophile as well as simultaneous breaking of carbon Br bond. When your nucleophile will attack on your carbon of your substrate, at the same time this bond, carbon Br bond, undergo partially cleavage. So if you observe the next step, there is a partial bonding between carbon and OH, at the same time partial breaking of carbon Br bond. So if you observe this state, it contains the carbon having 5 different groups. So your nucleophile is negatively charged, Br is negatively charged. So the full negative charge over the OH group get distributed in the transition state between OH, carbon and Br. Now carbon is attached to 5 different groups. So this is the transition state. Now we have to check the features of this Sn2 mechanism. So If you observe this, attack of nucleophile and breaking of carbon pair bond takes place simultaneously. So that's why it is a single step mechanism with simultaneous bond breaking between CBr and bond forming between COH. Then as your Br is present on front side of your molecule, the OH group, which is again negatively charged or having more than electrons in its valence shell, such a nucleophile will attack from backside because both are negatively charged. So front side is blocked by Br group, so it will attack from backside. So backside attack is possible. There is no attack from front side because this Br group which is present on front side get repel this incoming OH group from front side. So only backside attack is possible, and this also avoid the steric repulsion or steric hindrance. What is steric repulsion? Repulsion due to bulkiness of the groups OH and Br minus, and it also avoid the electrostatic repulsion between the incoming nucleophile and the leaving group because both are negatively charged. And next point is about the transition state. So in transition state, the nucleophile and leaving group are bonded to carbon with partial bonding and carrying partial negatively charged. So it is denoted by -half on OH as well as Br. And if you observe that transition state, there are 5 different groups attached to your center carbon, 3 hydrogen and 1 OH, 1 Br. So in this transition state, it contains penta-coordinated carbon having 3 sigma bond in one plane, making bond angle 120. They are carbon-hydrogen bonds, and 2 partial covalent bonds, that is CBr and COH. These bonds along a line perpendicular to this above plane. When this Sn2 reaction is brought about at a chiral carbon that we already discussed in optical activity topic, and the product is also found to have opposite configuration compared to that substrate. So if your substrate is having dextro configuration, your product is leo-rotatory, and if your substrate is leo-rotatory, your product is dextro-rotatory. So it opposes the configuration. So this is about the slower step. And in fast step, so first step is this one is slow step. This one is slow step. Slow step. And this one is fast step. Why this is slow step? Because there is an attack of nucleophile as well as breaking the carbon pair bond. So it takes time because your substrate is already stable, and so it is slow step, and that's why this step is also known as RDS, because rate of the reaction is depends on this step. So RDS means rate determining step, that is called as RDS step, and slow step is always RDS. And in fast step, there is a complete breaking of carbon Br bond at the same time complete forming of COH bond, that gives your product, that is methyl alcohol and leaving group as a Br minus. So this is about the Sn2 reaction mechanism. Now we have to learn about the Sn1 reaction mechanism. So if you observe Sn2 reaction mechanism, in slower step both your nucleophile and substrate will involve. That's why it is Sn2 reaction mechanism. Now if you observe the rate is equal to K into concentration of methyl bromide as well as OH minus. So it is a Sn2 reaction mechanism. Now we have to study about the Sn1 reaction mechanism. So S for substitution, N for nucleophilic, 1 for unimolecular. So if the order of this reaction is 1, then it is called as Sn1 reaction. So that methyl bromide is a primary alkyl halide, mainly primary alkyl halide follows Sn2 reaction mechanism. Now our example is tertiary butyl bromide react with your OH minus, and it shows product tertiary butyl alcohol and the Br minus. So here rate of the reaction depends only on concentration of tertiary butyl bromide and not the OH minus. That's why the reaction is Sn1 reaction. Now here we have to check some concept. So if you observe this reaction, the concentration of the substrate appears in the rate equation. So it is studied by kinetics, and the concentration of nucleophile OH minus does not influence or does not affect on the reaction rate. So tertiary butyl bromide react with hydroxide ion. It follows two-step mechanism, and in slow step the CX bond in the substrate, undergo heterolysis. As halogen is, Br is more electronegative. It carrying the electron pair away from the carbon along with it. So Br gives negatively charged and carbon carrying positive charge. And then it produces a carbon carrying positive charge, that is carbocation, and then in next step, which is the fast step, there is an attack of nucleophile. So in slow step, in the substrate undergo hydrolysis. In fast step, there is an attack of nucleophile. Now let us see the mechanism of this reaction. So this reaction mechanism takes place in two steps. So here tertiary butyl bromide, which is the substrate, in which C-Br bond undergo cleavage, and there is a formation of this planar carbocation with leaving group Br minus, and in next step the attack of nucleophile on your carbocation to produce your product, that is tertiary butyl alcohol. So this what is the features of this Sn1 reaction? It is a two-step, just now we studied. And first, there is a heterolysis, means breaking of C-Br bond undergo in unsymmetrical manner. As Br is more electronegative than carbon, Br goes along with electron pair. As there is a breaking of C-Br bond, it takes time, so it is slower one, and this can be reverse again when Br minus attack on your carbocation, because your carbocation is a unstable species. It is unstable. That's why it takes time and it is slower one. This, if you observe this carbocation intermediate, it is planar. All the three CH3 group and your carbon which carrying a positive charge are in the plane. So it is planar one. Then in next step, second step, the attack of your nucleophile on your carbocation is a faster one. Why? Because your unstable species is there and OH minus can easily attack from both sides, front side as well as back side, to give your product. So now to see the next point, when we carried out this Sn1 reaction with chiral carbon, means carbon which having 4 different groups, that is in optical active substrate, the product form is nearly racemic, because just now we see that your carbocation is planar one and you can attack your nucleophile from front side. If there is attack of nucleophile from front side, the configuration is retained. Means if your dextro is the alkyl halide, your product alcohol is also alkyl halide. Your product is also dextrorotatory, and if your alcohol is levorotatory, your product is also levorotatory. So retention, and if it is attacked from back side, then there is an inversion in configuration. So if this attack of nucleophile is equally possible, so if 50% molecule will attack from front side and 50% molecule of nucleophile will attack from back side, so we form 50% dextrorotatory product and 50% levorotatory. So mixture of them gives racemic mixture. So both the enantiomers of the product, that is dextro and levo, are formed along with almost equal amount, and that's why there is a racemization. The nucleophile can attack planar carbocation from front as well as back side. So draw the Fischer projection. You can draw the Fischer projection of this molecule and write down the two products when this compound A react with nucleophile OH minus. So simply replace this Br by OH, and if you write the mirror image of this, then this Br on left hand side, this CH3 on right hand side, that is the enantiomer of this, and simply change the position of Br in your mirror image and replace the Br by OH, that gives your product, and these are the, and then write down the mirror image of that is the enantiomer of your product. Then draw the Fischer projection formula of the product form when this compound B, that is 2-chlorobutane, attacked by OH minus. Now there are certain factors which influencing the Sn1 and Sn2 reaction mechanism. So why methyl bromide is a compound which undergo Sn2 reaction mechanism, why tertiary butyl bromide undergo Sn1 reaction mechanism, that we have to check by using some factors. So first factor is nature of substrate. So if the transition state of Sn2 reaction mechanism is observed, then that carbon is attached to 5 different groups. Out of that, 3 are hydrogen, one is OH and another is Br. So it is crowded. We already seen that in diagram. So you can check that diagram also again. Here this transition state is crowded. There are 5 different groups. So Sn2 reaction mechanism is favored in primary alkyl halide and least favored in tertiary halide. Then if you observe the Sn1 reaction mechanism and if you observe a carbocation, this carbocation, if you observe, it is planar and it has no steric crowding. So only 3 methyl groups are there and there is no overcrowding. So bulkier alkyl groups can easily accommodated in the plane. So all these 3 methyl and this center carbon are in the plane. So as a result, Sn1 reaction mechanism is most favored in tertiary halide and least favored in primary halide. So if you observe the planar carbocation intermediate results in relief from steric hindrance present in the tertiary alkyl halide substrate. So if you observe here in Sn2 reaction mechanism, this transition state of that methyl bromide. So carbon is attached to 3 methyl, 3 hydrogen and 1 nucleophile and 1 X. So penta coordinated crowding, and if instead of this hydrogen, if there is a methyl group, 1 methyl group, 2 methyl group and 3 methyl group, so crowding over that carbon goes on increasing and that destabilizes the compound. So primary alkyl halide favor Sn2 reaction and not the tertiary alkyl halide. And if you observe the Sn1 reaction mechanism, if you observe methyl carbocation and then this ethyl carbocation, isopropyl carbocation and propyl carbocation and tertiary butyl carbocation. So number of alkyl group increases, that increases the electron donating inductive effect of methyl group, which stabilizes the carbocation, carbon carrying positive charge. They share the carbon carrying positive charge, as well as one methyl group having 3 CH alpha bond. So that also helps by hypoconjugating structures. So in ethyl carbocation there is 1 methyl group, so we can write 3 hyperconjugating structure. In ethyl carbocation there are 6 hyperconjugating structure, and in tertiary butyl carbocation there are 9 hyperconjugating structure. So all these things will stabilize the carbocation. So this is least stable methyl carbocation and this is most stable tertiary butyl carbocation because it is planar one. All are planar, but no doubt, but in tertiary butyl carbocation there is a more inductive effect as well as more hypoconjugating structures. So there are 3 methyl groups, there are 3 inductive effects by 3 methyl groups, and there are 9 hypoconjugating structures. That's why this is more stable carbocation. So if you observe Sn1 reaction mechanism, primary alkyl halide, for example methyl alkyl halide, it is not favored, but tertiary butyl bromide is favored for Sn1 reaction mechanism. Then so here that same order is mentioned. Methyl halide Sn1 rate increases from primary to tertiary, and Sn2 reaction rate increases from tertiary to primary. And secondary halide reacts by either of mechanism or mix of mechanism, depends on that conditions. The next factor is nucleophilicity of the reagent. So all are familiar with nucleophile. You can write the examples of nucleophile. They are electrically neutral. Water, there are 2 lone pairs. Ammonia, there is 1 lone pair, and in KOH also there are 2 lone pairs. There are some examples of anionic nucleophile, OH minus, X minus. So what is the difference between the base and nucleophile? You can find out the answer. So what is nucleophile? It is a species that is use its electron pair to form a bond with carbon. It is itself electron rich. If observed in water, there are 2 lone pair over oxygen in water. There is 1 lone pair over nitrogen in ammonia. Or if you observe anionic nucleophile, the negative charge is there, so they are electron rich and they will attack on electron deficient species, and they are also called as Lewis acid. So Lewis acids are those substances which donate a lone pair of electron. So if you observe the nucleophile, if there is a more powerful nucleophile, it easily attack on your substrate, as well as the attack is faster and it favors the Sn2 mechanism. So powerful nucleophile is must. Then in case of Sn1 reaction mechanism, as nucleophile does not participate in slow step, there is no role of that nucleophile. If it is absent, it does not affect on the rate of reaction. So it is rate of the reaction in Sn1 reaction mechanism is independent on the nature of nucleophile. Then so if you observe this reaction, your question is the negatively charged nucleophile is more powerful than its conjugated acid. So if you observe above reaction, ROH plus water gives RO minus plus H3O plus. ROH here it accepts a proton, so it is acid 1. Water donates its lone pair, so it is a lone pair donor, so Lewis base 2. Then if ROH donate names are different, so I have to change this. So it donate the lone pair, it donate the proton, so proton donor is Lewis acid, and it gives, after removing the H, RO minus, and when water that accept H plus, it gives H3O plus. So only the difference between acid and its base is of only H plus. So that pair is called as conjugate acid base pair. So a negatively charged nucleophile is more powerful than its conjugated acid. So this RO minus, which is a nucleophile because there is a negative charge, so this base 1 is more powerful than its conjugated acid ROH. Or we observe that H2O is more powerful nucleophile than H3O plus. Then when donor atoms are from same period of the periodic table, the nucleophilicity decreases from left to right in the period. For example, water is less powerful nucleophile than ammonia. When donor atoms from the same group of the periodic table, nucleophilicity increases down the group. For example, I minus is better nucleophile than Cl minus. The next one is the solvent polarity. Sn1 mechanism proceeds via formation of carbocation intermediate. So a good ionic solvent, that is polar solvent, stabilizes the carbocation by solvation. The solvation of that carbocation is relatively poor, and solvation of anion Br minus is particularly important. Anions are solvated by hydrogen bonding. So if you observe Br minus, get, because it is more electronegative, it get stabilized by solvating with hydrogen bonding of your solvent. So, and that is protic solvent. Protic means there are positively charged, negatively charged present in your sample. That is called as protic solvent. So Sn1 reaction proceeds more rapidly in polar protic solvent than aprotic solvent, because in Sn1 reaction mechanism there is a carbocation and leaving group. But if you observe, polar protic solvent usually decreases the rate of Sn2 reaction. So in RDS step of Sn2 reaction mechanism, substrate as well as your nucleophile is involved. So if there is a protic solvent, your nucleophile gets stabilized by your protic solvent. So instead of attacking that nucleophile on your substrate, it gets stabilized. So reaction does not favored by Sn2 reaction mechanism. So there is no need of polar protic solvent for Sn2 reaction mechanism. Better way we have to follow a protic solvent for this type of mechanism, that is Sn2 reaction mechanism, which is favored for it. So remember this, for Sn1 reaction mechanism you have to use polar protic solvent, and for Sn2 reaction mechanism you have to use low polarity or aprotic solvent. So if we observe our questions regarding to this, which of the following two compounds would react faster by Sn2 mechanism and why? If you observe this compound, it is 1-chlorobutane and it is 2-chlorobutane. So if we remove this chlorine, then carbon this CH2 carrying positive charge, and if we remove this chlorine, this CH carrying positive charge. So this, after removing the Cl, 1-chlorobutane gives primary carbocation and 2-chlorobutane gives secondary carbocation. So in Sn2 reaction mechanism, penta-coordinated transition state is involved, and the order of reactivity of alkyl halide toward the Sn2 reaction mechanism is always primary, then secondary, then tertiary, because in this order there is a decreasing crowding in the transition state from primary to tertiary, as 1-chlorobutane is a primary alkyl halide and 2-chlorobutane is a secondary alkyl halide. So most favored is the 1-chlorobutane for Sn2 reaction mechanism. So simply you have to understood which is primary, which is secondary, and according to that you can write the answer. So one more question is, how are alkenes are prepared from alkyl halide? So when we use alcoholic KHARGE, then alkenes can be obtained. So you can write the reaction at home, and which is stronger base from the following. This is another question for you, which is your exercise question. Then one more question is, primary allylic and primary benzylic halides shows higher reactivity by Sn1 mechanism and other primary alkyl halide explained. So Sn1 reaction involve primary benzylic halide shows higher reactivity by Sn1 reaction mechanism than other primary alkyl halide. So in Sn1 reaction mechanism, if there is a formation of carbocation intermediate and if it is stabilized, then it favors that mechanism. So if you observe this allylic carbocation, this allylic carbocation can be stabilized by resonance, or if you observe this benzylic carbocation, it also stabilized by this resonating structure. So if carbocation was stabilized by resonating structure, then it favors Sn1 reaction. If it is not stabilized, then it does not favor Sn1 reaction. So in this way, we will understood the concept, mechanism, Sn1 and Sn2.